So because the inverse square nature of the electric field, any location where the field is 0 must be closer to the weaker charge. In this case, it's Q2. And you consider magnitude when it comes to charges, not just positive or negative. So also in between the two charges, the fields due to the two charges are parallel to each other and cannot cancel. Thus, the only place where the field can be 0 are closer to the weaker charge Q2, but not in between the two charges. So the electric field here, E, is going to be equal to K, which is 1 over 4 pi epsilon naught. It's going to cancel, so we're not going to worry about that really, times the magnitude of the charge Q2 divided by the distance squared, which is x here, minus K times the charge Q1 divided by D, the distance between them, plus x squared. And we want to know where the electric field is 0, so this is going to be equal to 0. Okay, so then we find that Q2 magnitude here, we're not considering positive or negative, times D plus x squared is equal to charge Q1 times x squared. Therefore, x is equal to the square root of the magnitude of Q2 divided by the square root of Q1 minus the square root, again, magnitude of Q2 times the distance between D. So this comes out to equal 18 centimeters. And this is to the left of charge Q2. So this we can write left of charge Q2. And box that in as our solution for part A. Okay, start a new page for part B here. So the potential due to the positive charge is positive everywhere, and the potential due to the negative charge is negative everywhere. So since the negative charge is smaller in magnitude than the positive charge, any point where the potential is 0 must be closer to the negative charge. So we're going to consider the location between the charges, position x1, and to the left of the negative charge, position x2 here. So the potential V1, where it's 0, is going to be equal to K, which is 1 over 4 pi epsilon naught, times Q1 divided by D, the distance between, minus the position x1, plus K Q2 divided by x1. And of course, this is equal to 0. So solving this for x1, we find that x1 is equal to Q2 times distance D divided by Q2 minus Q1. This is equal to 1.6 centimeters. Okay, and then where the other potential V2 would be equal to 0, this is going to be K times Q2, this time not magnitude. The charge positive or negative value of the charge matters here. So D plus x2 plus K Q2 divided by x2. And of course, this is a point where it's equal to 0. So solving for x2, we find that x2 is equal to negative Q2 times the distance between D divided by Q1 plus Q2. We find that this comes out to equal 8 centimeters. Okay. So then the answer here, and we'll just go ahead and maybe type this out. It's going to be a distance, we'll call it x, so it'll be distance x1 from negative charge towards positive charge. So that's one of the ways to think about it. Or the other one would be distance x2, which was 8 centimeters, from negative away from positive charge. Where, of course, x1 here is equal to 1.6 centimeters and x2 is equal to 8 centimeters. We can box that in as our solution for part B.